Okay, so I suggest we start. So welcome to this data visualization module. So my name is Laurent. I'm Professor of Bioinformatics at the UC Louvain in Belgium. But before we start, I would like to introduce the sticky notes that I always use for teaching, so that those that were here last week are already familiar with how this works. So I'll pass these around. So if you take one of each, please, and then pass it to you later. So we have two core sticky notes. We have this that vaguely looks like red, and then this one that looks like green. I might mess up the colors. I happen to do that very regularly, but from the context you will know what color I mean. So this color means it's good, you understand, and for example when we do exercises you are happy to move on to the next exercise, the next part of the course. And when you do that, let's say you do an exercise and you're happy with it and you understood, you're happy to move on, and you can then paste it like this on your laptop screen. On the other hand, however, if there is an issue, especially if, for example, you don't understand the question, chances are if you don't understand the question that somebody else in the room hasn't understood the question, maybe because I did a bad job at explaining it, then please use the other color and put it like this on your laptop. And that will help me to very quickly assess whether we are making good progress or not at all. Okay? And these two pieces of information are extremely important, because if I see one red sticky note, that's fine, I will go and try to help the person. If I see 2, 3, 4, 5 red sticky notes, clearly there was something wrong on my part, and we really need to move back and explain, clarify misunderstanding. And if I see that the majority of you use a green sticky note, that means, okay, it's good, we can move on, and maybe check with a couple of people that haven't finished yet. Now, having said that, and also during the lecturing, don't hesitate to use red sticky note if you want to raise a point. You're always free, of course, to raise your hand and interrupt me and ask questions anytime. But if you don't think it's the right time, feel free to use the sticky note. Or I have lived many years in the UK, and people, the Brits are sometimes a bit embarrassed to interrupt somebody. Might not be your problem, but they find it sometimes a little bit difficult. So sticky notes are really useful for that. Okay? So this module is called Visualization of Biomolecular Data, and the material is available online under this short URL here, biomol.this. So as a kind of motivating example, I wanted to show you this data that by now you all know very well, because I already showed it last week for the people that were here last week, and the previous speaker showed the very same data. That's the famous Wisconsin data set. And if we look at the data, we don't see anything special. If we look at summary statistics, we don't see anything special. If we look at some kind of statistics, the residuals from our linear modeling, we will see that something is wrong, but clearly nothing beats the visualization. Okay? If we look at the data, they're very striking, interesting pattern that will be highlighted instantly. We will use the very best tool that we have to assess these patterns, which is our brain. So the focus on this course is, and I'm going to quote two terms that the previous speaker used: insight. Okay, get some insight in the data, understand the meaning of the data. That will be the focus of this course. We are not going to focus on producing nice-looking figures. For example, on using the right colors. Using the right colors is extremely important. That's not what we are going to focus on. I think it's at the end of today. Yes, Stephen Brown will come and do presentations about the right use of size, colors, forms, and so on. Okay, so this is not what we are going to focus on, not because it's not important, but we need to pick our balance. Okay, so we're not going to spend too much time with that. But hopefully, And by the end of today, you'll have the right tools to be able to generate your own figures and then adapt the colors or any kind of patterns based on what you want to do. So the beauty of the figures that we will try to generate are not necessarily interpreted, will not be assessed with the kind of the visual eye candiness of the figure, but rather can we understand, can we extract some meaning from these figures. Now, another really important point is that to be able to produce these visualizations, we need to be able to manipulate data. Okay, visualization is hardly producing a figure, but a lot of the work comes beforehand, and it's manipulating these data sets. And so today we're also going to learn some tools to be able to manipulate, calculate summaries of these data that eventually we will want to plot. And something related to that, to the data manipulation, and eventually its visualization, is data structures. So some data, well, data comes in many different shapes and sizes, and some of these shapes will, well, first we don't necessarily always choose the shape of the data we get, but some shapes, some data structures will be very convenient to do one thing, and other data structures will be much more convenient to do other things. So if you want to learn how to visualize data, we need to learn how to manipulate this data, and we need to have an understanding of the different types, different shapes of data that we can get, so that we can transform them from one to another, we can manipulate them, and then eventually produce the kind of data structure that we want for the right data visualization. So that's the program for today. And so to get an idea of how much time we should spend on these different topics, I was wondering if you could let me know how familiar you are already with R. So could you use your green sticky notes if you are familiar with R, and by familiar you mean at least you took last week's introduction to R statistics course, and the red sticky note in case R is completely new to you. Okay, very good. And so how familiar are you with dplyr and the kind of tidyverse tools to manipulate data? So could you leave your green sticky notes out if you're familiar with it? This, and if you took the course last week, I will consider that you have already some familiarity with it. Okay, and same question with ggplot2. If you have some familiarity with ggplot2, green sticky note, otherwise red sticky note. Okay, so apparently you are all already familiar with today's material. Good, so we'll see how it goes, and I will not completely ignore that material, but I might just present it very quickly and then give you some time to apply these to some exercises. Okay. So we're going to use a set of packages today and tomorrow and on Wednesday. I think you have already installed all the packages. If not, we will be able to install them whenever we need them, but otherwise there is this script that you can source. It's on the first page of the lecture material. And that should install everything that is needed for the whole duration. So we're going to use RStudio. So we're going to start by firing up RStudio here. And so what I'm going to do is I'm going to create an RStudio project. And at the beginning of every session, I'm going to reopen that RStudio session to make sure that I am always using the same working directory and always find the data that I have stored and generated or downloaded. I assume that I I guess if you all know RGGPlugins and so on, you're all familiar with RStudio and RStudio projects. If there are any questions, please don't hesitate to ask them. So I'm going to do a new project, new directory. Here we go. I'll call this simply viz. And I'm going to create it in my home directory. And here we go. I'm also going to immediately create a data folder. So you're going to download different data sets, and I'm going to put these in the data directory, and so I know that's where I'll be able to find them later on. And I'm going to start by creating the first script. I'm going to immediately save it as S01, so I'm going to call my scripts S01, S02, S03, and so on throughout the sessions. And then, either at the end of the day or at the end of the workshop, I'll create an archive of that R project, and I'll leave it on the Google Drive that you should have access to, so you have everything that we wrote here together. But by all means, please do the same thing and write your own script. And feel free, of course, to organize them as you see fit. And so, given that this first session here is about data, exploring the kind of data structures that we will have to analyze in high throughput biology, I'm going to call this first script as 01 data. Okay, so we'll do a copy and paste. So to start with, I'm going to load kind of a meta package called tidyverse. It's going to load a set of packages that we will need several times throughout this course, including a package called dplyr to manipulate the data, ggplot2 to visualize the data, and then also a package readr here to read data in tabular, in text-based spreadsheets. Okay. So I'm going to read the first data in. It's the IPRG data set. It's a quantitative proteomics data set. Okay, here it is. And it contains spiked-in proteins into a yeast background. And it was developed as part of the ABRF initiative. And these quantitative data were distributed to many different labs. And these different labs were asked to analyze these data and identify the proteins that were differentially expressed, these spiked-in proteins that were spiked in at different concentrations. So the protein names were anonymized, and different labs had to identify these differentially expressed spiked-in proteins. And so the data.
From where did you copy this data?
So if you type this line of code, so all the data sets are available online, and they all have short URLs. So they will all start with bit.ly, and then they will all start with this biomet data something, and the one that we want to read in now is IPRG CSV. And so this is a link to a CSV data frame, CSV file, and read_CSV, we read it immediately online. Last week we had this file, but locally in our data directory, and here we're going to read immediately from that URL. If you want, you can, of course, also copy this URL, and it is true for all the data sets that we are going to use. And this points immediately to the CSV file. So you could also download that CSV file in your data directory. Yes, and maybe during the next break, what I can do is to maybe download all the data that we're going to use and put them on an archive file on the Google Drive. So in case of network failure, we'll have local. Or if you download it, you'll have the local copy. Everything okay? So if everything is okay, could you remove your red sticky note? Okay. Otherwise, you'll draw attention. So here is this. Just a second, I'm trying to make the screen a bit larger. Yeah, okay. So here's how this data set looks like. We have 7 variables, 7 columns, one with a protein identifier. We have 2 variables with intensities. We have a log2 intensity and a raw intensity. We have the ROM, or the raw file acquisition, where that specific protein was identified and quantified. We have 4 different conditions, named condition 1, 2, 3, and 4. We have biological replicates, 1, 2, 4, and we have technical replicates, A, B, and C. And so this data set can be generalized like this. Where along our rows we have a set of observations, and along our columns we have some variables. And in each variable we have one and only one piece of information. And that means that in every cell here, we can start to generalize these kind of data sets and to reason on these data sets that comply to this definition where we have observations on the rows and variables on the columns, and that every cell contains one and only one piece of information. And if we're interested in one variable in particular, we can extract that column and we will get all the observations or the values for that variable for all the observations. So in this case, here we are, we have 36,421 rows observations and 7 variables. So I'm going to take a subset of this IPRG, I'm going to call it IPRG2. And I'm only going to take the 1, 3, and 6. These 3 rows of interest, the protein, the ROM, and the intensity. And so I'd like to transform this data into a different type of table. Do you know if we have an eraser for the whiteboard? I'll go and look. So the data that we have at the moment looks like this. We have proteins, 1, 2. We have ROMs. Oh. Chalkboard, so it's fine. Where are these?
It should be fine.
Okay. And then ROMs. I'm going to call ROMs A and B. And then we have an intensity here Take the third one. Okay, so 1, 2. So 1, yeah, and so B, A like this. And then we have intensities. I'm going to call this X, 1A, X, 2B, and so on. So this is called a long format. And indeed, the example table that we have here is pretty long. It has 36,000 rows. There is another type of data structure that is used a lot in high throughput biology, and that would look like this, where we have still our 2 proteins, 1 and 2, but now along the columns we have our samples, or our ROMs, A and B, and each cell contains now X, 1A, 1A, X, 2A, X, 1B, X, 2B. And typically, these data sets here are called the wide format. It's not very wide here because we have very few samples and very few proteins. But these ones tend to be much wider and not that long. And we are going to see a couple of advantages of these long and wide data sets thereafter. So the question is, how can we transform the example that we have on the left-hand side to the structure that we have on the right-hand side? And so we're going to use a function called spread to do that. Because the data is very thin here, thin and long, and we want to spread it over more columns. So what do we want to spread? Well, we want to spread our IPRG data set. And so the first thing we need to define is, how do we want to name the new columns here? Well, these new columns will be named based on a variable that exists already in our data set, and this variable is ROM. So here we define what is the key that we want to use to name the new columns that will need to be created upon spreading that data set. And the next information that we need to provide is, well, what are the values that we are going to use to populate this new spread data set? And these values are stored inside a variable, and that's the intensity. And I'm going to call this IPRG3. Execute it. Execute this, IPRG3. And here it is. Yes?
Is that part of a package spread?
Spread is part of the dplyt package.
Okay.
That is one of the packages that is loaded automatically.
TidyR, actually.
Or TidyR. That is part of all these packages loaded with tidyverse. If you want to know where a function comes from, you can always type its name. And what you'll see is the code of that function. And then here at the very bottom, you see environment namespace tidyr. That means that that function is defined in the tidyr package. Or looking up that function's documentation. So let's view IPR3. And here it is. So it's indeed much wider. And we only have 3,027 entries from the original 30, 36,000 or so rows. Okay, and so here we have these 30 columns, new variables, including the protein name here and the 12 runs, 12 samples.
Can I ask a question?
Yes, of course.
So we are subsetting the main data set, main data set, right, IPRG, in different ways.
Yes.
So in the third data set, IPRG3,
Yes.
what are we splitting here? Because initially we had 7 variables in the original data set.
Yes.
Now it became 13.
Yes.
So what exactly is the spread function?
So we had. So the reason I only look at 3 columns here is because these are the 3 columns that we are most interested in.
Right.
Okay. We'll see later how to combine even more information. So we started with.
Those were the protein names, the run IDs, and the intensity.
Exactly.
Right. And
So
then
we
for the third one.
started with, this is IPRG2.
Right.
Now, we want to re-encode exactly the same information, but under a different data structure. And that's what I call IPRG3. So we have exactly the same information that is stored, but using different formats. So these are the large versions of what I showed here. We have 2 proteins in 2 samples. For each of these pairs, protein run, we have an intensity, x1a for protein 1 in sample A. We have here also 4 intensities, but they are re-encoded so that all the proteins are featured along the rows and the samples along the columns. And so these are 2 fundamentally different ways of thinking about the data, and some are really useful for some applications. So this data structure is really useful for some applications, and this data structure is useful for other applications.
So why is the number of columns increasing in the IPRG3? Now we have 30 variables
Yes.
in the columns. Why is that?
Okay, so let's do one, 2, right, and sample C.
Okay, so we have different categories.
And now we have sample C here. So we have 1 column for each sample plus the proteins. And we could check this if we look at IPRG, PRG2 $run. So we extract the run. And let's look at unique. We only want the unique runs. And indeed here we have 12 unique runs. There was another question? So one of the features that I find really interesting of the wide data set, the one on the right-hand side, is the following. We can ask, are there any missing values in IPRG3? If, for example, protein 1 was not quantified in sample C, so we still would have 2 and C, this is something that is immediately visible on this data set. And here I ask, are there any missing values in IPRG3? This is not something that is necessarily visible in this long data frame. So to explore this a little bit, let's try to now convert. So what we did here, transforming this one to the wide one, was spread. What we're going to do now is to convert the wide one to the long one, and that's called gathering. So let's gather data from IPRG3. So how do we want to gather this data? We still have a key argument and a value argument. So now we have the column names, but these are now going to be transformed into a new variable that we will want to call ROM. And then now all the intensities here will be converted into a new variable that we're going to call intensity. Let's not forget, however, that in our dataset IPRG3, here, there is this protein column that's still there, so we'll have to handle it automatically. Oh, by the way, very often in these wide datasets, I forgot to mention, we would not have this column with protein names. We would use this one, the protein names, as row names of this matrix or data frame. We want to focus exclusively on the quantitative data. So the new name, or the name of this new variable that we want to create would be RON. If we want to keep exactly the same structure as we had before, the new value would be intensity, but we need to specify that the protein column present in IPRG3 here should be excluded from this gathering of all the quantitative values into the new intensity. Yep. So I'm going to create IPRG4 here and execute it. And you can view IPRG4. And here it is. Very similar to what we had initially. I say very similar because it's not exactly the same. And the difference, here we have a difference in the number of rows between IPRG2, which is the original long data frame that we had, and the new one, the one that we created from the wide data set. And this difference stems from is.NA. So I have this data frame, and I ask which of the cells of this data frame are missing values, and then I sum all these values. All the trues will be converted to 1, and all the false, all the cells that do not have a missing value are converted to 0. If you try to do operations of logicals, true becomes 1 and false becomes 0. So here I have 3 values in this wide data frame that are missing. And so when I converted this back with my gather, I kept these missing values, whereas they did not have these missing values in my original data set. And so an example that I have here, protein 1 sample C, protein 1 sample C, I either have my missing value, or I do not have my missing value at all. That means I have a row that is missing. Yes?
So why do you have to point out to ignore protein in the gather function? Is that respect?
Yes. So here's the wide data set. And I need to say, well, which are the values that I want to gather to create these new columns? Well, these values are actually all the values in my table. There are additional samples here on the right that you can see. But protein, these are not the quantitative values. This is a kind of a column of its own with metadata that should not be gathered to create a new intensity column.
So
Yes?
I have a question. So, our RP, like the third data frame we created, how does R know that run are the column names? Like the key is the run, but how is that specified in this data frame? I don't know if that question makes sense. But like we're gathering with the run names, but that's not specified in this data frame, is it?
No. So when we moved, at what time? So if we look at this one,
So yeah, we're in the Y data frame, right? And then
Yes.
we're gathering it with the key equals run.
Yes.
But how does R know what run is?
automatically these will be the column names that will be used to create a new variable.
Right, no, but how does it, like, 'cause
How
it's
does
not-
it know?
How does it know that the
That
column
we-
names are runs, I guess? Like, because you could have created the run on as the rows, right? Before.
No, when we gather, we always want to gather into a tidy data set. And so our variables always become columns. That's kind of defined.
Okay.
We are not going to gather and then create new rows. Rows are reserved for observations.
Okay. Yeah.
So we want to gather all these keys, which are the names of the columns of my sample
Okay.
here.
I see.
That is defined.
That's defined.
If now you wanted to change that data set again, and for example have one row with runs, then you would want to transpose that data set, which you can do with the function t, which we are going to see in a minute.
Thank you.
Right, and so if we, here in IPRG4, we ended up with additional rows that contain missing values, which is something that you might want or not. If you don't want it, there is an NA.rm argument that we have already seen last week that we can set to true, and so it will automatically ignore these rows that will end up with a value here being intensity, that is missing. But note that IPRG4 here, if we have these missing values, we could find them, we could look for them, but it wouldn't be automatic to immediately get information where is this missing value, what protein is it in, what sample is it in. We could, if we read information up, so if I'm back here, 1, C, and A, so if I find, here I have a missing value, I see that it's protein 1, sample 1, C. But it wouldn't be as straightforward. We would need to do analyses to figure out, for example, let's say I have protein 3 here, X3A, X3B, and maybe another missing value here. Okay. With this representation, I can very quickly, for example, spot that I have missing values for sample C. Okay. Or if I had another missing value here, I could quickly spot that, something is weird with my protein 3. That's the protein that seems to accumulate missing values. Okay. So again, this is something that we could, of course, compute with long data frame. But I think it's interesting to realize that these different data sets have to. And, sorry, I wanted to call this 5. So I'd like to use now a different data set to introduce a different type of data structure. So let me come back to my data here. And that's this CRC data set, and I'm going again to create it and read it in online. And it's a data set that has information, quantitative information for 200 proteins. Yes? 200 samples. And this contains quantitative information for a set of proteins, including some spiked-in proteins, case 1. But in addition to that, we view this table, so CRC data frame. So here we have our first gene expression for 200 samples and so on. And then if we move towards the right, yes. Okay, I'm not sure why I don't see this in the view here. But columns 73 to 74 will give me information about these different samples. So an identifier for my 200 samples, shown here along the rows, my groups, age, gender, and then a cancer stage. So here we have it's clearly not a tidy data frame, because if we take one row, not sure if we can consider this, or maybe we could consider this an observation. We have one sample. Yeah, maybe it is. Maybe it's a kind of tidy data set, but it's not a long one, where every column has it's a mix. Every column is a variable, but it's not, strictly speaking, a long data frame as we tend to have when we talk about tidy data sets. So using this data set, I would like to introduce a new data structure that is important in high throughput biology, whether that's proteomics, RNA-seq, or others. And this data set can be represented like this. First, we have a matrix like this one, when we have our features, proteins, genes, transcripts along rows, and we have our samples along the columns, exactly as we have seen here, and we have only quantitative data in here. This is a convenient data structure, but it misses a lot of information, and in particular, each of these features generally comes with a set of annotations. So for example, this first feature here we have quantitative values for all of our samples, but I would like to have its identifier, UniProt identifier, for example, maybe a kind of a longer description of that protein, if it's a protein. Maybe I would have some information about the gene ontology, okay, for that protein. And for example, something that we'll calculate later on, we might also have a p-value. So every row here in this quantitative feature, that I'm going to call my expression matrix, every row here has one row of metadata that is associated to it. And we have the same thing for the columns, where each column that represents a sample has here another vector describing information about these samples. So for example, P1A1, I think it was one of the sample identifiers that we had here, P1A1. Well, for example, this would be female, would be cancer stage 1 and age 32. Maybe the second sample here would be a male, stage 2, age 41, and so on. So in addition to the quantitative data, we have two associated tables that provide annotations for the features and annotations for the samples. But the important thing here is that these are not stored as 3 independent tables. We could do that. But they are stored as one variable of a specific type or specific class that would have been coded, developed by package developers specifically for the analysis of these kind of quantitative values. We can have a quick look at one of these data structures. For example, sorry, let me move back to my script here. So Amazon base is one of the packages that defines this data structure that is found across any omics domain. And I'm going to load one of these data sets called Amazon set here. So this tells me that I have 55 features, 55 rows, and 4 samples, 4 columns. I can extract the quantitative data. Here it is. Here are my features, so these don't have meaningful names because these are PSMs, and this is an iTrack data set. But these could have meaningful names if we wanted. So here, this corresponds exactly to the white IPRG data set that we had before. But it's only one small part of this more complex object. And we can access that quantitative part with a function called EXPRS. So we ask to retrieve the expression data from this more complex data structure. If we wanted to extract the documentation about the samples, so if we call this XPRS, very often this is called maybe P data or phenotypic data or call data, and this one would be called F data for feature metadata, or often also called raw data. So if you want to extract this very specific subtable, we would ask, give me the phenotypic data that is stored inside this Amazon set, and if we wanted the feature annotation data, we would use the F data function. Let me view it here. View. So here it is. We have 55. Yeah, you can see this. 55 rows, one corresponding to each of the quantitative values, and each of these rows has a spectrum identifier, a protein accession, protein description, a peptide sequence, this PSM, the spectrum was allocated, and so on. So this allows us to store quite a bit of information in a structured way. So this does not correspond directly either to this long or this wide data set. The quantitation data corresponds to a wide data set, and these data sets correspond to typically long data sets. But the point I would like to make is that these data are also tidy. If tidy data means a data set that we can reason, and that's data. There are some assumptions that need to be met independently of the actual nature of the data, but we know exactly where to look for some specific information. We know exactly that if we want to access data, we can use EXPRS, and then there every row corresponds to a feature, every sample corresponds to a sample, and if we take the fifth row EXPRS, we have the quantitative values for a feature. If we take the fifth row of F data, we have all the annotation for that one. And you're all familiar with the square bracket operator to do the subsetting. Well, this generalizes to these more complex data structures. So here, for example, if I say MSN set features 1 to 10 in my first dimension and 1 to 2 to my second dimension, I obtain a new MSN set with 10 features and 2 samples, but there is a guarantee that the subsetting will be done on all my different data structures in a consistent way. Excuse me, do you have a question?
No, I just have a game complicated.
But, if you want to create these MSN sets, and the CRCDF, the data frame that we have here, is a very good candidate to create these different data sets. The first thing you need to do is to extract the different subparts. Okay? In the CRC data set, we have this information and this information that are kind of contained in one large table. We have this and that are together next to each other into one long data frame. And this is arguably, based on experience, not necessarily the easiest format to work with. So one thing that we might want to do is to say, well, let's extract the different bits and pieces of this CRC data frame. And, for example, create a new MSN set based on these data sets, or these subparts of the CRC data set. Okay? So the first thing we know about the CRC data set is that columns 1 to 72, so my rows 1 to 72 contain information, quantitative information. Okay. From 73 onwards, it's documentation, annotation of my samples. That's already something difficult to, if you want to do data analysis, that's already something that is in the way of your data manipulation. Okay, this kind of boundary between 72 and 73. Before that, you have quantitative information, and after that, you have information about your samples. So, the first thing we could do is to say, well, let's create a new variable, E, that CRCDF. Let me write 1 to 72. Clear? So this contains my quantitative data, only the quantitative values in this CRCDF. But it's not quite what we want, because here our features are along columns. Typically, in high throughput data, biological data analysis, we tend to have our features along rows. So in addition to extracting 1 to 72, what we also want to do is to transpose this part of the CRC matrix. And as we had a question before, transposing is done with the T function. So let's have a quick look at quantitative data, where we have, we have proteins on the rows, and we have our samples on it. So 72 proteins, 200 samples. So what we are also going to do is to add call names of E. Currently, we're going now to arbitrary labels these samples 1 to 200. So if I look here, E 1 to 10, 1 to 3, for example, here it is. This is a subset of my wide data set with my features and my samples. Okay. This is, in terms of high throughput biology data analysis, known territory. It's exactly like the IPRG 3 that we created. And this corresponds to the expression part of our kind of omics data container. And that's why I called it E. The rest of our columns, 73 to 79, to phenotypic annotations of samples. So I'm going to create a new variable that I'm going to call our CDF. It's going to contain, let me check how many columns I have, 79. So this is going to be 72. 79. Let's look at it. PD 1, 2, 5, 1, 2, 3. For each sample, we have a set of annotations. So now, in this data set, there is no annotation for the features. This is typically something that we might want to calculate. If we did hypothesis testing to conditions, we could get a p-value for each feature. But in this case, we don't have this. So let's create this MSN set structure, and we can do this with a function called read MSN set 2. There is also read MSN set 1, but it's not. And so what we want to feed it in is a data frame contain the quantitative values E, and we specify that, this is done with the parameter E called, that 1 to 72, so actually all the row names, sorry, answer 2, all the row names here should be taken to create the MSN set. It's not 1 to 72, it's 1 to 200. So I have 72 features. I'm going to create CRC, for example. So here is CRC, and I can check my sample names. Yeah, these have been converted automatically from 1 to 200 to x1, x2, x3 because the name starts with number. And I also have feature names. Yeah, these are the original protein names. And I can now, I have this, my sample. I need to make sure that, move this down, I need to make sure that my row names here match exactly names. So the naming of this object, the names here must correspond exactly to the names of the columns here, and similarly the names of this data must correspond exactly to the names of this one to keep internal consistency of the raw data. Yes, tables don't have names anymore, but we can ignore this for now. Or can we not? I don't. So I am not sure whether we can ignore this for now. So we're going to convert this as data.frame. Without typo. Annotation of all my samples, and I can add this CRC CRC. So I had my CRC MSN set, but now I want to decorate it to add phenotypic information that is stored in this data frame. It allows me, for example, to extract specific contains. For example, if I look at CRC dollar, for example, group. Okay. I have groups here on CRC. So I can start to make queries on this data set. Which of my columns belong to group CRC? And as I have 200 of these, this is the vector of logicals of length 200, which I can then use, for example, to subset my original data set. So the fact that we have everything contained into a single object allows us to access to the quantitative data, but also do the specific subsetting, in this case along the samples, the columns, but we could do the same thing along the rows. And we're going to see some examples later on, for example, for specific visualizations. So we're going to use different data sets throughout the course. And these will either be as these data containers, either for proteomics data set or microarray or transcriptomics data set. And sometimes these will be in the long format or maybe in the wide format. And depending on what we want to do, we will need to be able to convert them from one to another. So here's another example data set, highlighting the importance of having access to different data structures. And here we're going to use, I don't remember, a library called ALL, and the data called ALL, shown here, contains information for 100 patients that suffer from acute lymphoblastic. So here these 108 samples, patients, and we have quantitative information for 1,206.25 individual genes. Okay. So this was produced with affirmatrix microarrays. And set, it's not called an MSN set like the CRC, but they are really the same. Oh, sorry.
Can I just give you the option? Because I missed some of the variables. Yeah. The two arguments above, sorry.
Above here?
Yeah.
is is that the one?
Sorry.
Um,
Thank you.
CRC dollar group.
Yeah, that's the one.
So this command goes into the CRC dataset and extracts information about the group, sample group types. In my CRC dataset, somewhere here, there is a column called group that is either healthy CRC, healthy CRC. And so this is a shortcut to say, well, give me this sample annotation, variable group. Then I want to query which ones corresponds to CRC. And it will return a logical, a vector of logical corresponding to the number of samples I have, the number of columns that I can immediately reuse to subset my own. Which is exactly that state. In terms of subsetting, we have first dimension corresponding to the number of rows, and the second dimension corresponding to the number of columns after the column. Famous data set that has been around for a long, long time. Here's the annotation that we have for this data. Here along the rows contains all this kind of clinical annotation. And we're going to the more wild annotation. And so this is exactly notes. So what we want is all the data sets. We want only to keep the samples that are annotated with negative or BC or BBL. And grab those that have a type B. This allows to create a new subset. So we still have the original data as an ALL variable, but this allows us to create a new subset of 79 samples of interest. Okay. Define these two. So I'm not going to the details of this as the task. I am simply going to copy and paste this code that uses very well-known package called limma. I'm going to execute this. A package called limma that is aware of the fact that this omics data is stored into this omics data container. So lots of people, computer scientists, statisticians, have devised new methods how to analyze these data. And these new methods are meant to be working with these well-defined data containers. And so here I define what the experimental design of my test. Here are a set of codes that actually model and execute the model to calculate these values, these p-values between the two groups. And eventually, here I'm going to update the feature data, the row annotation of my ALL subset. And the details of the analysis are not one here. That's not what we focus on. What we are going to focus on is the fact that the results of these analyses, so for each of these G's here, is stored as part of the object here in the feature metadata, which is something that is extremely important for some visualizations like this that we're going to generate probably tomorrow. And so some statistical tests calculate some new features, each of these new variables, each of these describing rows that we store as part of this feature variables. And it include a log-fold change and an average expression, a t-statistic, p-value, and then just p-value, and here's another statistic that's computed as part of the lemma analysis. So even though these lines of code are now taken for granted, what they do is that they add annotation to our omics data set. And these annotations, these new variables, we want to store them with the data. We want to take them with us throughout all the kind of exploratory data analysis that we are going to do. It's something that is kind of baked into these data containers, so they have advantages. But clearly, if we want to use ggplot2, it is this kind of data that we will need. So we have done the conversion from one type of data to one, or among these two. Very often when you have your data here, you might want to extract some bits as a long tidy table, for example, to use. Unfortunately, I don't think we came up with the perfect structure that fits use case. Have this spread and gather and function read in a sense of two that allows us to convert. And to obtain this, I should have started saying this, this data set, so you can immediately put it. I'm going to copy and paste this code here. Table. So with some code, we can download the file. And so this pre-formatted AL BCR-NEC dataset with all the statistical results is already pre-computed and is available at this URL, bit.ly visbiomet data. It's always the same prefix, and then it's called ALL_BCR-NEC. And we want to download this data set inside the data directory in our project. And so we need to specify the two file names here. Now in my subdirectory of my visualization project, I have this RData file that I can load now or tomorrow when we'll start to produce plots and things like that. We'll then just need to load it directly, this file, from this directory. And so throughout the, actually tomorrow, and we'll about practice or specific tools, and by tools really I mean some type of visualization of data transformations. Different data sets highlight some specificity of visualizations that we want to use. So I don't know if you have, you probably have seen this figure that Hadley Wickham generally uses to kind of illustrate what he considers to be data science. So we have data, and typically data need to be transformed. Needs to be modeled, needs to be visualized, and we tend to iterate over and over again through these three aspects. There can be many more. It's some sort of simplification, but clearly there is hardly only one step of these different three parts, and eventually we want to communicate our results. So what we are going to focus on are, in some respect, these three aspects where we want to transform the data, we want to visualize what's the effect of this transformation, we want to do some modeling, and by modeling here, calculating p-value would be some sort of modeling of our data, dimensionality reduction or clustering would be some sort of modeling, and we will want to visualize these. And depending on what data we have, we might convert these to one data structure, from one data structure to another. And unfortunately, from the data tidying, strictly speaking, if you get random variables, they are not elegantly formatted, to say the least. Even this transformation from one data structure to another is something that can take a considerable amount compared to what might look like the most exciting bits in particular visualization. And so what we are going to this figure here is maybe a zooming in inside these three parts that we are going to look at, especially tomorrow. So if we focus on quantitative mass spectrometry data, we will have raw data. So tomorrow we'll see some of the tools that we can use to parse raw mass spectrometry data. It actually would not be in any of these, strictly speaking, data structures, but would be something that is associated to this generic omics data structure, MSN set or expression set that we have seen, or two examples thereof we have seen. After quantifying and identifying these raw data, we will end up with expression data as MSN sets, expression sets, or long or wide tables. Okay. So in terms of raw data, we'll see how to access, visualize individual spectra, chromatograms, or possibly extract ion chromatograms. Once we have expression data, here are the kind of analyses and transformation that we might want to do. We are not going to focus on pathways, but we are going to look at differential expressions and visualizations thereof, missing values, visualizations thereof. Of course, we can also visualize and get a lot of information about the experimental designs using visualizations. Look at the variability within these expression data, and look at the effect of transformations such as normalizations on these expression data. And somehow these skills that we want to acquire to visualize biomolecular data in general and quantitative mass spectrometry in particular should allow us to adapt or apply these skills, whether we are on the raw data side or on the expression data side, and apply all these different types of visualizations on this data. And somehow, if we want to do it, and we know what we want to do it and how to do it, whether we have quantitative data, whether it's proteomics, transcriptomics, it doesn't really matter. Okay, so there are techniques that we would like to know, and then we will apply them, and then we can apply them, we can spend extra time to make the figures particularly nice, particularly beautiful, and possibly adding a layer of interactivity, which is something that we're going to look at on Wednesday. Yes?
How do you make that linear?
Oh. In LaTeX. In LaTeX. LaTeX is typesetting software or language. Are you familiar with Markdown?
Yes.
Well, Markdown is the kind of stripped down version that allows you to get stuff done, where you have relatively limited, but more than enough ways to format your document, while LaTeX is the overblown version of that.
More expressive.
Yeah, but kind of not as welcoming. LaTeX has been around for a long, long, long time. It's a brainchild of somebody called Donald Knuth, very famous computer scientist.
How do you spell that?
Oh, also L-A-T-E, chi, so it's not an X, it's a chi. And in there is a language that allows you to define a box here, a box there, and then I want arrows, I want dotted things. And so it's kind of, it's programmed if you want. Yeah, yes. And I can have a look later and find the code for that version. Okay, so I think yes, I tend to be a little bit late, so people that took the course last week know that they need to remind me when it's time to stop. So please don't hesitate, at least this time. We are on time. So the plan for after lunch would be to go through, and I think maybe this can be done relatively quickly. So just give a high-level overview for those that maybe have already seen ggplot2 but haven't had time. Then maybe what we could do is have more time to apply on some of these data sets. I have some exercises to kind of visualize these using dplyr and ggplot2, and also how to convert data from one to another. Okay, so maybe we'll try to focus on giving you time to do the exercises and then checking that all together. Now. Yes.
Download the library call.
Oh yeah, good point. So that's because ALL is, thank you for highlighting this, very good. It's a bioconductor package. I'll explain bioconductor a little bit more later on, but so you are probably familiar with CRAN, which is the main comprehensive archive network where all the packages come. But bioconductor is kind of a subset. Bioconductor was started by one gentleman, one of the two original authors of ARP. That is kind of the set of packages that are dedicated to the analysis and comprehension of high throughput biology data. And so to install bioconductor packages, you need to first install the packages. Another package is called BioC Manager. And that one is available in CRAN. And so when you have BioC Manager, you can use the function install from BioC Manager to install any packages, in particular packages from bioconductor. So this function uses install packages under the hood, but it's aware that there is not only CRAN, there are other packages, other repositories. And so if you say BioC Manager after installing BioC Manager like this, BioC Manager install ALL, and it will install packages from bioconductor. Having said that, this also works for other packages. DevTools or ggplot2 and so on are on CRAN, so you can use BioC Manager install to also install packages from CRAN. And you can also, Thomas P85, patchwork. You can also use BioC Manager install to install packages from CRAN. So for example, at the end of later today, we'll use one package called Patchwork by Thomas, who did a PhD in proteomics, interestingly, but he works now at our studio, that allows us to kind of combine ggplot2 figures with a nice and fancy syntax. And so if you specify a username and a package name, this function that uses now DevTools under the hood will be aware that it's a package from GitHub by default. And so if you use BioC Manager install, you can install packages from bioconductor, from CRAN, or from GitHub, which is convenient. Right. So that's it. Thank you very much. And so we start back at 0.130.